Hello everybody. It's a great pleasure to give this talk on the Approx conference today. So this talk is based on the joint work of myself and Anastasia Sideropoulos. Both of us are from the University of Illinois, Chicago, and the title of the talk is Computing Bi-Lipschitz Outlier Embeddings into the Line. First of all, let me talk a little bit about metric embeddings, what they are and how to handle them. Metric embedding is a map from one metric space to the other metric space, and we would like to, in a sense, preserve some of the structure of our initial metric space. As an example, let's look at this graph. The metric we are imposing on this graph is our usual shortest path distance metric, and we would like to embed it into the line. We can do it like this or like that. You can construct many of these embeddings yourself, but we would like to pick the one which is actually good because there are a lot of them. What does being good mean for an embedding? There are several different notions of that. One could think about additive distortion, additive error in the distances with respect to the initial metric space, or multiplicative error. This current work considers multiplicative error, multiplicative distortion. Let me talk about that a little. To introduce the multiplicative distortion, first we need to talk about the expansion of the map. Expansion of the map is, roughly speaking, by how much does our map stretches the distances. For instance, this first embedding has expansion at least 5 because the distance between V1 and V3 in the image is 5 and in the initial graph it is 1. One can check that this is the biggest expansion this map has. Also, there is a notion of contraction. By how much does our embedding shrink the distance? For these two embeddings, it doesn't shrink the distances. The contraction is 1, both of them, but it could be not 1. Finally, to get the distortion, we just take the product of expansion and contraction, and we would like to find an embedding which minimizes the distortion as much as possible. So, for instance, in this graph, as I said already, the biggest expansion we have is 5, contraction is 1, so the distortion of this embedding, embedding G, is 5. For the second embedding, well, we have an expansion 2 for the vertices V1 and V3, and also we have an expansion of 1.5 for the vertices V4 and V3. Contraction is 1, as I said, thus the distortion of this embedding is 2. We can conclude that in this particular case, we can quantifiably measure that the second embedding, embedding F, is better, does a better job in preserving the structure of initial space. The question of metric embeddings has been studied before, and I just would like to give a brief and by no means complete exposition of some more or less recent algorithmic work, which provides nice examples, nice results about algorithms and complexity of approximate embeddings. First of all, there has been a work done by Badu et al. In 2005, and they provided an opt-square approximation into R1 for graphs. Furthermore, Nairi and Rochelle in 2015 showed that there exists actually a constant approximation algorithm. However, the time depends exponentially on the optimal distortion, and the base of the exponent is a stretch of a metric. This is the ratio between the largest and smallest distances within the metric space. Sorry, not a stretch, a spread of the metric. What's next? Unfortunately, things are never too easy, and here is some hardness result. Even for d equals 2 for the plane, the embedding into the usual Euclidean plane isn't hard to approximate within the rational factor of n. So this is bad news. However, what if we want to sacrifice some of the points in our metric space? For instance, if we threw out some of the points, I don't know, logarithmic factor of it perhaps, will it become better? Here is a positive result, on the other hand, about inadditive distortion and outliers. Sideropoulos and Wang give a bicriterial approximation algorithm for embeddings into RD, with the additive distortion though. In the current work, we would like to consider a case where we embed a graph into the line. What is the motivation behind this? Well, first of all, graphs occur naturally while learning a manifold. If the manifold is nice enough and we sample the points uniformly and random from this manifold, then the shortest path metric on the induced graph will approximate the geodesic distance of the manifold pretty well. Why the line? Well, sometimes we would like to find some structure in the input in the data we have. For example, a line would represent a one-dimensional subspace in the input data. And finally, why do we care about outliers? Perhaps we know that these points, that there are some points which were added by an adversary, by a malicious adversary, and really messed up the distances in our input. We would like to get rid of them. As a toy example, here is a manifold, just the curve on the plane. Let's say we sampled some points from it, like this. So the points which are connected by a line, it means that these 2 points were sampled from somewhere close. For example, these few points represent this part of a curve. So far the shape really looks like the one we initially had, but let us assume that an adversary just added just 1 point here and connected this point to a few vertices, 5 vertices in our graph. If we are about to guess what is the shape now, we will get something which looks like this flower, which is pretty far from the initial object we had. Let us take a closer look on what are outliers in our case. For instance, here is a pretty horrendous graph, which looks like anything but a line, more like a bicycle. So just for the sake of assumption, let's say that this leg is really long. This path has length theta of n, where n is the number of vertices in the graph. The cycle is also large, on the order of number of vertices, and this wheel right here is very dense, has also linear order of n vertices. Okay? So intuitively, it must be hard to embed this object into a line, because here is a topological hole we have. Here are a lot of vertices on a have small distance to each other, etc. But if we look at these 2 vertices and then remove them and look at what is the new metric space induced by the removal of these 2 vertices, we can see that this is actually a collection of 3 paths, which has a distortion 1 embedding into a line because it is a collection of segments. So by removing of 2 outliers, just 2 vertices, we transformed this pretty complicated graph into a very simple object. Let me formally state what does it mean for a metric space to admit a KC embedding into some other metric space. K and C are integers. K represents the number of outliers and C represents the distortion. We would like to think about K and C as being at most sublinear in the number of vertices in our graph or in the number of points in our metric space. So the metric space admits a KC embedding into some other metric space if there exists a subset of our points in the metric space such that if we remove these points and look at the induced metric, then the induced metric space admits a C embedding into UNu, C embedding with respect to the multiplicative distortion. And the cardinality of our outlier set of our K is at most K, the parameter we give. One way to think about the outlier embeddings is to try to picture what can go wrong. How can it happen that our graph doesn't admit a low distortion embedding? One could go about it by listing all the possible abstractions, and that actually turns out to be the approach, and there are not so many of them. One abstraction is high density region. It means that the graph contains a ball such that this ball has a lot of vertices relative to the radius. A canonical example of this object would be a star graph. Also, for example, a clique, a complete graph. Here, a ball of radius 1 centered at the center of the star, for example, contains just all the vertices inside the graph. And intuitively, why is it hard to embed it into the line? Because no matter how we list these vertices in the line, there will be some of these leaves of the star which will end up very, very far from the center. The second abstraction is large metric cycles. This is an object which is a little more fancy than the usual cycles. It turns out it's not enough to consider only the graphs which contain large cycles. What we also need is that the cycle should be decomposable into relatively long paths which have large distances between each other. Or, another way to say it, the graph has to have sort of a large hole inside. Because again, if we're going to unlink this hole, then it must be that two of the vertices located on this cycle will fall far apart relative to what their distance was in the graph. Now, the third one is large metric tripods, or sometimes they're called spiders. What are those creatures? Well, if we have a central vertex and at least 3, could be more, long legs hanging from it, then this is also an unembeddable type of the graph, and an unembeddable with low distortion. Why? Because some of these vertices located close to the center will end up very far from the central vertex in the embedding, but they were at a constant distance from it to begin with. Interestingly enough, this observation about the abstractions turns out to be quite fruitful, because elimination of these abstractions provides us with an algorithm. First, we reduce the density of a given graph. Then, we eliminate metric cycles in the resulting structure. Afterwards, the structure resembles a forest in a sense. We remove large metric tripods from this forest, embed a resulting graph into an actual forest, and then embed a forest into a line. The resulting space of outliers, set of outliers, is the union of the outliers obtained from the density reduction, cycle elimination, and tripod elimination. And here is the main result of the paper, which basically says for a graph G and non-negative number K and positive number C, there exists a polynomial time algorithm which, provided with J, G, K, and C, gives one of the two outcomes, exactly one of the two outcomes. It either correctly decides that G does not admit a KC embedding into the line, meaning we cannot find a set of points, a set of vertices of cardinality K into our graph, such that the removal of these points induced a subgraph which admits a C embedding into the line, or it outputs some other set, which upon removal gives us an embedding of G into the line. It outputs both this set and the embedding. As always in life, there is unfortunately a caveat for what I just said. This caveat being that what if we remove some set of vertices? Sure. And what about the embeddability of the induced structure? What if the graph we started with had a really low distortion, really a small set of outliers and a low distortion, and the graph we get after we removed high density objects from our graph, the induced subgraph, will not admit a low distortion? So an example of this would be a grid graph. Grid graph admits a constant distortion embedding into the line without any outliers. We just traverse a grid. However, if we remove two central slits of our grid, we will essentially get a large cycle, which has a distortion theta of n. Well, that's bad news. Nonetheless, there exists a single vertex. For example, this one, in fact, it could be any vertex in the cycle, which upon removal gives us just the line. So this observation can be generalized into the following statement we called repairing lemma, which basically says that if a graph was embeddable with low distortion and small set of outliers to begin with, then if we remove any subset of the vertices from the graph, the induced subgraph will still have a relatively small embedding, small distortion embedding into the line with a small set of outliers. Of course, the particular set depends on the graph itself, and it is different from the set we initially had, but we don't mess up the embeddability of an object by deleting a set from it. Now we are equipped with a repairing lemma we can use to patch our graph when we deleted some of the abstractions I've talked about, and we can take a closer look on how we actually get rid of them. First one is density reduction. There are two notions of density. One is more general than the other. The first one being a local density, that is how many vertices are there inside a ball centered of a vertex given a radius of this ball. The canonical object, canonical graph with high density is a star graph. Another one to think about is a clique. Unfortunately, it might be not enough to consider only the local density, because there are graphs which are not dense given a constant radius, but if we take a look at the global picture, take R being equal to the diameter of the graph, we actually get a high density object. That is like, for example, a binary tree, a graph which is very densely packed. We would like to get rid of these regions. How do we do that? It turns out it is enough to recursively sparsify the graph. Given our graph, we first check what is its density. If it is high enough, we compute a balanced vertex separator of the graph, remove these vertices from the graph, and recurse of the connected components we obtained. Once the algorithm terminates, we set the set of outliers which are responsible for the density as a union of all the vertex separators we deleted. And the repairing lemma guarantees that this set is not going to blow up in size. To deal with the remaining two abstractions, we need to introduce another object into our pantheon. That is Voronoi partition and something called a Voronoi miner. Let me show you in the example what this is. Consider the following graph. And to obtain a Voronoi partition, we would like first to specify a set Y with respect to which we are going to produce the partition. Let these three vertices be our set Y. Every cluster in the Voronoi partition contains exactly one vertex from I, and moreover, each of these clusters also should contain a nearest neighbor of V in Y. If we have ties, we break them arbitrarily to ensure connectivity. So the collection of clusters we obtain after this process is called a Voronoi partition with respect to Y. Now, an object which is related to that is called a Voronoi miner with respect to Y. How do we obtain a Voronoi miner? Well, we take our set of terminals Y as vertices, and then for every two clusters which are connected in our graph, initial graph, for example, the cluster of Y1, this cluster is connected with an edge with the cluster centered at Y2. In such a case, we draw an edge in the Voronoi miner. And we do that for every pair of connected clusters, Y1 and Y3, Y2 and Y3. In this case, the Voronoi miner with respect to Y is just a little triangle. What it allows us essentially to do is to zoom out our graph to look at the bigger picture for topological holes or tripods. All right, now equipped with the Voronoi partition technique, we are ready to handle the cycle elimination. To do this, first we compute an O of C net of our graph, that is the collection of points which are at the distance of O of C from all the other points in the graph. After that, we compute a Voronoi partition centered at the points of the net, and then compute a Voronoi miner, meaning contract each of the Voronoi cells to its terminal point. If a resulting structure has a cycle, then the initial graph was not embeddable in a line with low distortion, and vice versa. What we get is, as a Voronoi miner, is sort of a bird's eye view of our initial graph. And if this graph has a hole, then the initial graph had some unembeddable structure, and vice versa. So now what is left is to get rid of the cycles in the Voronoi miner. We compute an approximation for a feedback vertex set, that is the smallest set of the vertices which are enough to delete from the graph to make it to a forest, and we remove the corresponding Voronoi cells from the Voronoi cells which correspond to the terminals from the feedback vertex set from the initial graph. We set the union of these Voronoi cells as an outliers responsible for the cycle elimination. Now we can proceed to the final abstraction, that is the tripods. Roughly speaking, our graph now resembles a forest, and one other abstraction left which can prevent us from the low embedding are the structures with the common center and long legs. So first of all we find all of them. There are polynomially many, O of n to the fourth tripods, because each tripod can be specified by its center and 3 leg points, and we can just enumerate all of them. So for instance, on this picture, I counted only the relatively long tripods. For example, here is the yellow one, the red one, and the gray one. Shorter tripods for example, this one, they do not pose a serious obstruction for the embedding because we allow some small distortion. So that's done. Now we find the tripod centers. Roughly speaking, those are all the points which, upon removal, destroy at least one of the tripods, break it into a union of a forest of small diameter. After we found all of them, we create a set cover instantiation. That is, we are trying to find the smallest set of these tripod centers which we can delete and remove all the tripods from the graph. We can compute a log-n approximation to this set cover problem. In this case, just this one red central vertex is enough to get rid of all three of the tripods. And that's what we get. We set the outliers responsible for the tripods as a union of the Voronoi cells centered at the set cover of the tripod centers. Now we have just one final step. I'm cheating a little bit here because in the actual algorithm there is also a one intermediate embedding into a tree takes place. But essentially, because our graph sort of now looks like a forest, this intermediate embedding doesn't introduce much of a distortion. So we can think about our final structure as being a forest with no tripods. So we take each tree in the forest we have. In each of the trees, we find a longest path inside it. So here is the path P, and these triangles represent the subtrees hanging from the path attached to it. Now we would like to embed each of the subtrees into a line individually and then merge the embeddings together. How do we do that? For each of the trees, we construct closed subtrees. We construct a closed walk by doubling the edges right here. And then we just traverse this walk like this in order and embed each of the vertex we encountered on our way and keep the distance between the previous vertex we embedded and the current vertex we are embedding equal to their respective distance in the subtree. So for example, here the distance between them is 2, and in the embedding, why? Because we had to traverse this edge and this edge to embed these two vertices. We do that for all the subtrees and translate the embedding, keeping the distance between these two vertices. Here is the one in this subtree, and here is the root of the next subtree. The distance in the embedding gets translated by as much as what is their distance in the initial graph. After we've done this procedure, we're done. So that's it basically. Well, thank you so much. I hope you enjoyed the talk, and if you have any questions, please don't hesitate to ask them.